Hey, modern fans and followers, how are you? And your dear and near. It's activist teacher, Professor S. Suresh, back with altruistic enthusiasm for my 96th video on unreal of publication on YouTube today, 16th October 2020, Friday. Topic for discussion today is statistical quality control, SQC, tools and applications for quality improvement. Quality is basically fulfilling the customer expectations and exceeding the requirements to make them feel delighted, happy, excited. Quality control is a process by which entities review the quality of all factors involved in production. ISO 9000 defines quality control as a part of quality management focused on fulfilling quality requirements. This approach places emphasis on three aspects enshrined in standards such as ISO 9001, elements such as controls, job management, defined and well-managed process, performance and integrity criteria and identification of records, competence such as knowledge, skills, experience and qualifications, soft elements such as personal, integrity, confidence, organizational culture, motivation, team spirit and quality relationships. Inspection is a major component of quality control where physical product is examined or the end results of a service are analyzed. Product inspectors will be provided with lists and descriptions of unacceptable product defects such as cracks or surface blemishes, for example. Products have standards, also called as specifications. Inspection checks the manufactured product against those standards and classifies the product as good in conformance with the standards or bad, not in conformance with the standards. Quality control separates act of testing products to uncover defects from the decision to allow or deny product release, which will be determined by physical constraints. For contract work, particularly work awarded by government agencies, quality control issues are among the top reasons for not renewing a contract. The simplest form of quality control was a sketch of the desired item. If the sketch did not match the item, it was rejected. In a simple no-go procedure, however, manufacturers soon found it was difficult and costly to make parts be exactly like the depiction. Hence, around 1840 tolerance limits were introduced wherein a design would function if its parts were measured to be within the limits. Quality was thus precisely defined using devices such as plug gauges and ring gauges, basically limit gauges. However, this did not address the problem of defective items. Recycling or disposing of the waste adds to the cost of production. As does trying to reduce the defect rate, various methods have been proposed to prioritize quality control issues. Excuse me. And determine whether to leave them unaddressed or use quality assurance techniques to improve and stabilize production. Statistical quality control SQC was introduced in 1930s, total quality control TQC in 1956, statistical process control SPC in 1960s, company-wide quality control CWQC in 1968, total quality management PQM in 1985, Six Sigma in 1986, Lean Six Sigma in 2001. Statistical process control SPC is a method of quality control which employs statistical methods to monitor and control a process. This helps to ensure that the process operates efficiently, producing more specification conforming products with less waste, rework or scrap. SPC can be applied to any process where the conforming product meeting specifications output can be measured. Key tools used in SPC include run charts, control charts, the focus on continuous improvement and the design of experiments. An example of a process where SPC is applied is manufacturing lines. SPC must be practiced in two phases. The first phase is the initial establishment of the process, and the second phase is the regular production use of the process. In the second phase, the addition of the period to be examined must be made depending upon the change in 5M and E conditions: man, machine, material, method, movement, and environment, and wear rate of parts used in manufacturing process, machine parts, jigs and fixes. An advantage of SPC over the methods of quality control such as inspection is that it emphasizes early detection and prevention of problems rather than the correction of problems after they have occurred. In addition to reducing waste, SPC can lead to a reduction in the time required to produce a product. SPC makes it less likely the finished product will need to be reworked or scrapped. SPC was pioneered by Walter A. Sheward at Bell Laboratories in the early 1920s. Sheward developed the control chart in 1924 on the concept of a state of statistical control. Statistical control is equivalent to the concept of exchangeability developed by logician William Ernest Johnson also in 1924, along with the team at AT&T that included Harold Dodd and Harry Romick. He worked to put sampling inspection on a rational statistical basis as well. Sheward consulted with Colonel Leslie E. Simon in the application of control charts to munitions manufacturer of the Army's Picatinny Arsenal in 1934. The successful application helped convince Army Ordnance to engage AT&T's George Edwards to consult on the use of SQC among its divisions and contractors at the outbreak of Second World War. W. Edwards Deming invited Sheward to speak at the graduate school of the U.S. Department of Agriculture. Deming was an important architect of the quality control. He is a student of Sheward actually. Quality control short courses that trained American industry in the new techniques during the Second World War. The graduates of these wartime courses formed a new professional society in 1945, the American Society for Quality Control, ASQC, which elected Edwards as its first president. Deming traveled to Japan during the Allied occupation and met with Union of Japanese of Scientists and Engineers, JUSI, in an effort to introduce SPC methods to the Japanese industry. Sheward discovered the data from measurements of variation in manufacturing did not always behave the way as data from measurements of natural phenomena. For example, Brownian motion of particles. Sheward concluded that while every process displays variation, some processes display variation that is natural to the process, called common source of variation. Sources of variation. These processes is described as being in statistical control. Other processes additionally display variation that is not present in the causal system of the process at all times, called as special sources of variation, also called as assignable causes of variation, which Sheward described as not in control. In statistical control. In 1988, the Software Engineering Institute suggested that SPC should be applied to non-manufacturing process, such as software engineering process in the capability maturity model, CMM. The level 4 and level 5 practices of the capability maturity model integration, CMMI, use this concept. The application of SPC to non-repetitive, knowledge-intensive process such as research and development or systems engineering has countered skepticism and remains controversial. SPC is less effective in the domain of software development than, in example, manufacturing. Manufacturing quality is defined as conformance to specifications, as I mentioned before. However, no two products or characteristics are ever exactly the same because any process contains many sources of variability. In mass manufacturing, traditionally, the quality of finished article is ensured by post-manufacturing inspection of the product. Each article or a sample of articles from production of lot may be accepted or rejected according to how well it meets design specifications. In contrast, SPC uses statistical tools to observe the performance of the production process in order to detect significant variations before they result in the production of a substandard article. Any source of variation at any point of time in a process will fall into one of two classes: common causes. Common causes are sometimes referred to as non-assignable or normal sources of variation. It refers to any source of variation that consistently acts on process of which it is natural also, of which there are typically many. These types of causes collectively produce a statistically stable and repeatable distribution over time. Special causes are sometimes referred to as assignable causes of variation. The term refers to any factor causing variation that affects only some of the process output. They are often intermittent and unpredictable. Most processes have many sources of variation. Many of them are minor and may be ignored. If the dominant assignable source of variation are detected, potentially they can be identified and removed. When they are removed, the process is said to be stable. When a process is stable, its variation should remain with a known set of limits, that is called as tolerance limits, that is at least control limits in the control, that is at least at least until another assignable source of variation occurs. If the production process, its inputs or its environment change, the distribution of the data will change. The application of SPC involves three main phases of activity. First one, understanding the process and the specification limits. Second, eliminating assignable sources of variation so the process is stable. Monitoring the ongoing production process assisted by the use of control charts to detect significant changes of mean or variation. The data from measurements of variations at points on the process map is monitored using control charts. Control charts attempt to differentiate assignable special sources of variation from common sources, and also make sure whether the process is stable, whether it is in statistical control, whatever. Common sources, however, because they are an expected part of the process, are of much less concern to the manufacturer than assignable sources. Using control charts is a continuous activity ongoing over time. When the process does not trigger any of the control chart detection rules for the control chart, it is said to be stable in statistical control. A process capability analysis may be performed on a stable process to predict the ability of the process to produce conforming product in the future. A stable process can be demonstrated by a process signature that is free of variances outside of the capability index. A process signature is the plotted points compared to the capability index. When the process triggers any of the control chart detection rules, or alternatively the process capability is low, other activities may be performed to identify the source of the excessive variation. The tools used in these extra activities include Ishikawa diagram, design of experiments, and Pareto charts. Design of experiments are a means of objectively quantifying the relative importance, strength of sources of variation. Once the sources of special cause of variation are identified, they can be minimized or eliminated. Steps to eliminating the source of variation might include development of standards, staff training, error proofing, and changes in the process itself for its inputs. When monitoring many processes with control charts, it is sometimes useful to calculate quantitative measures of the stability of the process. These metrics can then be used to identify or prioritize a process that are most in need of corrective actions. These metrics can also be viewed as supplementing the traditional process capability metrics. Several metrics have been proposed as described in Ramirez and Ranger. They are a stability ratio which compares a long-term variability in the short-term variability, and ANOVA test which compares the within subgroup variation to the between subgroup variation, and an instability ratio which compares the number of subgroups that have one or more violations of the Western electric rules to the total number of subgroups. SQC, developed in the US in 1930 to 40 by W.A. Sheward and used for decades in American and Japanese companies. The basic approach consists of the following steps: awareness that a problem exists, determine the specific problem to be solved, diagnose the causes of the problem, determine and implement remedies to solve the problem, implement controls to hold the gains achieved by solving the problem. SQC is one of the most known and popular in the several process control methods. This technique is used to analyze a work process or its outputs, identify variations through date, take appropriate action in order to achieve statistical control, improve the capability of the process, capacity. The term SPC is sometimes misleading. Many people use it frequently to manufacturing process, whereas they're useful for improving results in other non-manufacturing areas. Sales and staff can be used in many of the activities and functions of service industry. A systematic way of problem solving. A process is a set of steps, causes, and conditions comprising activity that transforms input into outputs. The ratio of output to input is called productivity. Objectives of SPC are increase the ratio of output to input, reduce the variation in the way output of the process. For SQC, every process depends on gathering and analysis of data that what are profused in any organization that is involved in the process problem. The basic tools are data collection, data display. Data collection, a text sheet is useful in assembling and compiling data concerning a problem. It uses for data collection or view for any unwanted element. The functions of a check sheet are production process distribution checks, defective item checks, defect location checks, defect cost checks, checkup confirmation checks, data display. When a company collects data, it is converted onto various types of charts and forms for the purpose of display and analysis of data. Charts have different types as bar graph, present simple data and easy to understand. A scatter diagram is a relationship between two types of data. A histogram, distribution of data in terms of frequency. A Pareto diagram, statistical tool in problem analysis. Based on Pareto concept, vital, few, trivial, many. SQC, the use of statistical methods in the monitoring and maintaining of the quality of products and services. One method referred to as acceptance sampling can be used when a decision must be made to accept or reject a group of parts or items based on the quality found in a sample. A second method referred to as SPC uses graphical displays known as control charts to determine whether the process should be continued or should be adjusted to achieve the desired quality. Assume that a consumer receives a shipment of parts called a lot from a producer. A sample of parts will be taken and number of defective items counted. If the number of defective items is low, the entire lot will be accepted. If the number of defective items is high, the entire lot will be rejected. It's one of the acceptance sampling plans called single sampling plan. There are many other sampling plans. Correct decisions correspond to accepting a good quality lot and rejecting a bad quality, poor quality lot. Because sampling is being used, the probabilities of erroneous decisions need to be considered. The error of rejecting a good quality lot creates a problem for the producer. The probability of this error is called the producer's risk. The notation for that is alpha, normally in the diagrams. On the other hand, the error of accepting a poor quality lot creates a problem for the consumer in the market. The probability of this error is called the consumer's risk. The notation for this is beta in the charts. The design of the acceptance sampling plan consists of determining a sample size n and acceptance criterion C, where C is the maximum number of defective items that can be found in the sample and the lot can still be accepted. It is called as acceptance number. The key to understanding both the producer's risk and the consumer's risk is to assume that the lot has some percentage of defective items and compute the probability of accepting the lot for a given sampling plan. By varying the assumed percentage of defective items in a lot, several different sampling plans can be evaluated and the sampling plan selected such that both the producers and consumers' risks are reasonably low. SPC uses sampling and statistical methods to monitor the quality of an ongoing process such as production operation. A graphical display referred to as a control chart, provides a basis for deciding whether the variation in the output of a process is due to common causes, randomly occurring variations, or due to out of the ordinary assignable causes. Whenever assignable causes are identified, a decision can be made to adjust the process in order to bring the output back to acceptable quality levels. Control charts can be classified by the type of data they contain. For instance, an X bar chart is employed in situations where a sample mean is used to measure the quality of the output. Measure the quality of the output. Quantitative data such as length, weight, and temperature can be monitored with an X bar chart. Process variability can be monitored using a range or R chart. In cases in which the quality of output is measured in terms of the number of defectives or the proportion of defectives in a sample, an NP chart or a P chart can be used. All control charts are constructed in a similar fashion. For example, the center line of an X bar chart corresponds to the mean of the process, overall mean of the average of the subgroups of the process, and the process is in control and producing output of acceptable quality. The vertical axis of the control chart identifies a scale of measurement for the variable of interest. The upper horizontal line of the control chart refers to the upper control limit, and the lower horizontal line refers to as the lower control limit are chosen so that when the process is in control, there will be a high probability that the value of the sample mean will fall between the control limits. Standard practice is to set the control limits at 3 standard deviations above and below the process mean, because we assume the normal distribution for the variation, Gaussian distribution, bell-shaped curve. The process can be sampled periodically. As each sample is selected, the value of the sample mean is plotted on the control chart. If the value of the sample mean is within the control limits, the process can be continued under the assumption that the quality standards are being maintained. If the value of the sample mean is outside the control limits, an out of control conclusion points to the need for corrective action in order to return the process to acceptable quality levels. The 7 basic tools of quality is a designation given to a fixed set of graphical techniques identified as being most helpful in troubleshooting issues related to quality. They are called basic because they are suitable for people with a little formal training in statistics and because they can be used to solve the vast majority of quality-related issues. The 7 tools are cause and effect diagram, also known as the fishbone diagram or Ishikawa diagram. Check sheet, control chart, histogram, Pareto chart, scatter diagram, stratification. Alternately, flow chart or unchart. The designations arose in post-war Japan, inspired by the 7 famous weapons of Benkei. It was possibly introduced by Kaoru Ishikawa, who in turn was influenced by a series of lectures W. Edwards Deming had given to Japanese engineers and scientists in UC in 1950. At the time, companies that had set about training their workforces in SQC found that the complexity of the subject intimidated most of the workers and scaled back training to focus primarily on simpler methods which suffice for most quality-related issues. The 7 basic tools stand in contrast to more advanced statistical methods such as survey sampling, acceptance sampling, statistical hypothesis testing, design of experiments, multivariate analysis, and various methods developed in the field of operations research. The typical evolution in the use of statistical techniques in SQC can be summarized in the following way. At the lowest level of maturity, there exists only modest applications of acceptance sampling. When maturity increases, sampling inspection is intensified Next is SPC, when the systematic use of control charts already developed by users. When the process attains stability and maturity increases, it is then usual to develop different experimental designs and assess the reliability of the final product. This enables the improvement and optimization of production. The SQC at this moment much more than a set of statistical instruments. It's a global way of thinking of workers in an organization with the objective of making things right at the first place. This is mainly achieved through the systematic reduction of the variance of relevant quality characteristics. The SQC is nowadays routinely used in big organizations which, apart from the specific quality departments, have contracts with the researchers who facilitate the development of simple but more sophisticated procedures to ensure a better quality of the products. The Deming Prize is the longest running and one of the highest awards on TQM in the world. It recognizes both individuals for their contribution into the field of TQM and businesses that have successfully implemented TQM. It was established in 1951 to honor W. Edwards Deming, who contributed greatly to Japan's proliferation of SQC after Second World War. His teachings helped Japan build its foundation by which the level of Japan's product quality has been recognized as the highest in the world. Was originally designed to reward Japanese companies for major advances in quality improvement. Over the years, it has grown under the guidance of the Japanese Union of Scientists and Engineers, JUSE, to where it is now also available to non-Japanese companies, albeit usually operating in Japan, and also to individuals recognized as having major contributions to the advancement of quality. All of you know Japan is number one for quality. The award ceremony is broadcast every year in Japan on national television. In process improvement efforts, process capability index or process capability ratio is a statistical measure of process capability. The ability of a process to produce output within specification limits. The concept of process capability only holds meaning for processes that are in a state of statistical control. Process capability indices measure how much natural variation a process experiences relative to its specification limits and allows different processes to be compared with respect to how well an organization controls them. Since the process capability is a function of the specification, the process capability index is only as good as the specification. An effective quality management system, QMS, is not just one where good products and services are delivered. Rather, it is one that continuously seeks to improve the products and services being delivered and the corresponding delivery process used by the organization. In order to establish an effective QMS, the following characteristics are required: leadership, adopting a quality policy, instilling a culture that values quality, involving all levels of management in quality initiatives, identifying a senior quality management, providing resources and personnel to accomplish quality objectives, delivering products and services that always meet customer expectations, design quality and prevention, establishing a vision for the future of where and what the organization wants to be, and developing a plan to arrive at the destination. Long-term focus. Focus on customer satisfaction, clearly identifying internal and external customer requirements and making decisions that support the commitment to meet those requirements. Continuous improvement, identifying key areas for improvement, whether they are products and services or process. Teamwork, employee participation. All employees participate to the best of their ability and within the bounds of the areas of expertise to deliver products and services that meet requirements for performance, cost, and schedule. Training and development. All persons at all levels within the organization receive basic and advanced quality training related to the functional and managerial responsibilities within the organization. Six Sigma. Sigma is the standard deviation of the variation that occurs. Six Sigma has captured the attention of chief executive officers, CEOs from multi-billion corporations and financial analysts on Wall Street over the last decade. Michael Harry, president and CEO of Six Sigma Academy Incorporated, defines it as a business process that allows companies to drastically improve their bottom line by designing and monitoring everyday business activities in ways that minimize waste and resources while increasing customer satisfaction. Tandy et al. Calls it a comprehensive and flexible system for achieving, sustaining, and maximizing business success, uniquely driven by close understanding of customer needs, disciplined use of facts, data, and statistical analysis with a diligent attention to managing, improving, and reinventing business process. Contrary to general belief, the goal of Six Sigma is not to achieve Six Sigma levels of quality, that is 3.4 defects per million opportunities. This is again based on normal distribution. It is about improving profitability, improved quality, and efficiency are the immediate byproducts. Some have mistaken Six Sigma as another name for TQM. In TQM, the emphasis is on the involvement of those closest to the process, resulting in the formation of ad hoc and self-directed improvement teams. Its execution is owned by the quality department, making it difficult to integrate throughout the business. In contrast, Six Sigma is a business strategy supported by a quality improvement strategy. While TQM in general sets vague goals of customer satisfaction and highest quality at the lowest price, Six Sigma focuses on bottom line expense reductions with the measurable and documented results. Six Sigma is a strategic business improvement approach that seeks to increase both customer satisfaction and a company's financial health. Six Sigma seeks to improve bottom line profits by reducing the hidden costs of poor quality. Immediate benefits enjoyed by businesses implementing Six Sigma include operational cost reduction, productivity improvement, market share growth, customer retention, cycle time reduction, and defect rate reduction. Six Sigma begins by identifying the needs of the customer. These needs generally fall under the categories of timely delivery, competitive pricing, and zero defect quality. The customer's needs are then internalized as performance metrics. Example, cycle time, operational cost, and defect rate for the Six Sigma practicing company. Target performance levels are established, and the company then seeks to perform around these targets with the minimal variation. For successful implementation of Six Sigma, the business objectives defined by top-level executives such as improving market share, increasing profitability, and ensuring long-term viability are passed on to the operational managers such as yield improvement, elimination of the hidden factory of rework, and reduction in labor and material costs. From these objectives, the relevant processes are targeted for defect reduction and process capability improvement. While conventional improvement programs focus on improvements to address the defects in the output, Six Sigma focuses on the process that creates or eliminates the defects and seeks to reduce variability in a process by means of a systematic approach called the breakthrough strategy, more commonly known as the DMAIC methodology. DMAIC is an acronym for Define, Measure, Analyze, Improve, Control. The various development phases for a typical Six Sigma project. Principles of SQC, the principles that govern the control of quality in manufacturing are: control of quality increases output of saleable goods, decreases cost of production and distribution, and makes economic mass production possible. The quality of manufactured goods is variable within an upper trend under conditions of competitive manufacturing. The conformance of finished product to its design specifications and standards should be accomplished by avoiding the making of non-conforming materials rather than by storing the good from the bad after manufacturing is completed. Rice has pointed out that it is necessary to fit the organization and procedure of quality control to the situation in each plant. To do this, certain fundamental principles of SQC must be adhered to for success in applying these techniques to manufacturing process. Rice has stated the principles of SQC. Variability exists in every repetitive operation. Statistical methods enable management to determine what the expected or chance variability of a process is, and thus isolates the excessive variations due to an assignable cause from those due to chance causes. Those may then be studied for the cause and corrective steps taken. Wherever like products are turned out in quality, SQC techniques are applicable. A state of SQC in which an operation produces articles that remain consistently within the range of chance variations so that no assignable or findable cost is present is not usually found, where statistical control techniques are not being used. Quality must be built into a product. It cannot be introduced through inspection. In the words of W.C. Deming, not how much product, but how much acceptable product is what counts. A state of control must be established at a satisfactory quality level before maximum efficiency in the operation can be obtained. The control process to be satisfactory must produce a satisfactory average product as well as that does not vary from the average more than would be expected by chance. Following are the important benefits derived from the techniques of SQC. Lesser cost of inspection. SQC is based on sampling technique, which involves lesser cost of inspection, thereby cost of production is considerably reduced. Increase in profits by minimizing rejections. SQC ensures the production of standard products which bring higher profits for the producer. Setting tolerance limits. Quality control charts is clearly laid on the tolerance limits beyond which the product is to be rejected. Results shown by these control charts are more authentic and correct. Develops quality consciousness. SQC is greatly helpful in developing the feeling of quality consciousness among the workers working in an organization. This improves their functioning and reduces the number of defective operations undertaken by them. Enhances reputation of the firm by adopting the techniques of SQC. Predetermined quality of the product is achieved by them, and consumers get the desired quality products. This brings good name to the firm and increases its goodwill among the people. Improved relations between vendor and customers. It is greatly helpful in improving relations between supplier and the purchaser of material by clearly fixing the tolerance limits with regard to quality of the goods supplied. This minimizes the possibility of any dispute between both the parties. Besides above mentioned benefits, SQC ensures smooth and unrestricted production by removing breakdown of machinery and work stoppages, as it greatly helps in detection of the troubles soon, which are immediately corrected without delay. Quality control, quality assurance, TQM, QMS, Six Sigma have become essential for survival and sustenance of all organizations in manufacturing as well as service sectors. Teamwork is a must For successful implementation of these practices, the focus is on continuous improvements, flexibility, expandability, etc. Changes are constant, and all organizations should keep with the pace with the changes in the dynamic world and adapt these changes for their own betterment and ultimate success. Debates, discussion on open-ended topics like this can go on forever. Anyhow, let me pull the plug here. We'll meet again real soon with another interesting topic. Some of the statements used expressed are solely mine, based on limited knowledge gained over 6 decades of versatile experience. Always watch these videos with closed caption subtitles for absolute 100% comprehension as per my sincere recommendation. Zillion times so far. I strove to complete the presentation within 20 minutes max. It is a norm I had set myself to retain the viewer's attention, but nowadays I exceed the time limit by like 2 times, 3 times, because I make honest attempts to cover the topic more elaborately, including so many intricate fine details, referring a wide variety of sources, in particular Wikipedia quite extensively, besides articles and books published recently. Besides, of course, I sprinkle my own salt and pepper and season it with my personal experiences so far in my life and also intuition. Stay at home as much as possible to maintain social distancing attributed to the pandemic novel COVID-19 and prolong your lifespan. Lead a healthy life. God alone can put a stop to natural or unnatural events, maybe bio or cyber war events like pandemics, which may lead to apocalypse and the extinction of all sentient species on Earth for no fault of theirs. Rest in peace and harmony.